In this video, we're going to cover confidence intervals for the population mean. Okay. And specifically is what we're going to do, okay, is our goal will be to come up with an estimate for the population mean mu. Okay. And in order to do that, we're going to take a sample and we're going to find the sample mean. Okay. And that sample mean will be what we call the point estimate. But is what we're going to do is we're going to go out from that point to the left and to the right to create an interval. And it'll be an interval in which we essentially hope mu is in. Okay. And in fact, maybe let's come down here and make a little visual of it right next to where I have some information about confidence intervals here. So I'm going to sketch us one. So your confidence intervals are really just number lines here, okay? Or a section of a number line, maybe we should say. So is what the deal is this point estimate for us is going to be X bar. Okay. Okay. And we don't know how we're going to find it yet, but half of this distance here from here to here is called the margin of error. Okay. And that's how far we're going to go in both directions. So maybe I'll go, I don't want to do that. I'm going to just say margin of error here. Okay. And we can pick this margin of error so that 95% of confidence intervals will contain mu, or we could adjust it to maybe be a different width so that 99% of these confidence intervals will contain mu, and so on. Okay. And again, we'll cover how we'll come up with that margin of error here in a little bit. But this is what they look like. Okay. And again, the goal is hopefully mu is somewhere in here, okay, in this interval. Okay. So it's a range of numbers. Okay. We'll have a lower bound and an upper bound for these intervals. Again, they're a range. Let's see. Okay. All right. Well, let's see why it is the case if we have something called a 95% confidence interval, why 95% of confidence intervals will contain mu. Let's go look at a picture of that. Okay. So is what I have here is I have pictured two normal distributions. They're actually the exact same distribution on the left versus the right. Okay. And you can see we have mu, the population mean, in the center. Okay. And is what isn't necessarily clear because it's not labeled, but I have it highlighted up above here, which is that the shaded region that you see is where the middle 95% of sample means are going to land. In other words, that shaded region goes to the right about 2 standard deviations from the mean, and it goes about 2 standard deviations to the left of the mean, right? We learned the empirical rule at one point. We learned that approximately 95% of the data is within 2 standard deviations of the mean. Okay. And so now here's the next thing. Now that we have that part taken care of, and I'm going to highlight it. These things down here are confidence intervals. Okay. And is what I want you to see is that in one case, our sample mean X bar is within this range where 95% of X bars will land, right? It's in this region if I go up like that. Okay. While this other one is not within that area where 95% of X bars will land. Okay. And so the big thing here between these two, and maybe I'll highlight the other one just to keep it consistent. Okay. But the one on the left where X bar is within that 95%, notice that the confidence interval contains mu. Okay. Versus on the other side, if X bar does not land where 95% of X bars will land, okay, then notice the confidence interval does not contain mu. Okay. So this is something that we will actually need to worry about, but this also gives you a visual on kind of how this works. Okay. But yes, this does mean that 95% of the time we build a confidence interval, it's going to contain the true mean, mu, okay? And 5% of the time it won't. Okay. Now, again, that's based on a 95% confidence interval. We will have other levels of confidence that we'll work with, but 95 is a very common one. Well, let's move down and kind of reiterate some of the things we've already mentioned here. Okay. All right. So right here, we have a visual of what it would look like if multiple samples were taken. But I do want to note that the confidence intervals that I've sketched so far, those two up there and then this one here, they run horizontal, but you can have them run vertical as well. And all this means is that this would be the lower bound of one of the confidence intervals, and this would be the upper bound. But do notice that almost all of these confidence intervals have or contain mu, the population mean. Okay. So if we, again, do have a 95% confidence interval, that means 95% of the confidence intervals will contain mu. Okay. And that's exactly what we see here is in this visual, 5%, which is actually just one of the confidence intervals, doesn't contain mu. And then 19, which is 95% of the confidence intervals, do contain mu. Okay. And you might be wondering, well, why are all these confidence intervals different? Okay. Well, every time we make a confidence interval, we're taking a new sample and finding a new sample mean. Okay. So your confidence interval will always be centered at your sample mean, meaning that each confidence interval you make is going to look a little bit different. Okay. Now, do notice they all have the same width. They're just centered at a different spot. All right. So before we actually get into making confidence intervals, or maybe interpreting a confidence interval down here in one, there is one more thing I wanted us to mention. So I said right now that our point estimate is X bar. Okay. And X bar is the sample mean. Okay. And so this, again, this is a good estimate. Well, it is an estimate. I don't want to say it's a good one because it's not always going to be good. It is an estimate for the population mean mu. Okay. But we don't have to base this on means. We could do percentages instead. If we are maybe looking at the example, we'll have in example one where we're talking about what percentage of people say they'll vote for Clinton versus Trump in 2016. Okay. But this point estimate, we could also be talking maybe about the sample median and trying to estimate the population median. Okay. But yeah, for now, it just means. Okay. So let's come back down. But I just wanted to point out this one actually, this confidence interval doesn't deal with means, but the idea is the same. Okay. So here in example one, it says a Washington Post ABC poll, a Washington Post ABC News poll released October 16, 2016, found that 47% plus or minus 3.3% of people will vote for Clinton and 43% plus or minus 3.3% will vote for Trump. Interpret the meaning of Clinton's confidence interval, assuming it is a 95% confidence interval. Okay. So I still have us working with 95%. We'll look at a different percentage here eventually. Okay. So one thing you are going to notice here, probably in the news in the near future, is you're going to see estimates based on polling for what percentage of people will vote for each candidate. Okay. Sometimes they actually give the interval, like you see here. They'll say some number plus or minus something else. And other times they'll just report their sample percentage. Okay. The confidence interval, I think, is the better option, kind of indicating that there is some possibility for some error here. Okay. But I have here that we're just going to interpret Clinton's confidence interval, because if we do this a second time, it's going to look exactly the same. But here would be the idea. So if we are talking about Clinton here, we are working with this confidence interval. And yes, I am calling this a confidence interval. So it could be written like this. Okay. But it might be nice to know what the lower and upper bound are. So I can find those. So I'm just going to, for the lower bound, I'm just going to take that 47 and subtract 3.3. And for the upper bound, I'll add 3.3. All right. And if we want to, we can grab the calculator. So what we have, 47 minus 3.3 and 47 plus 3.3. And so if I scoot this over, we can see our two numbers here. So we have 43.7 and 50.3. And so we could interpret this really in two ways. Okay. So one way that you might hear this interpreted is the shorthand for the second way that maybe we'll write it here in a second. Okay. But let's see here. Okay. So for Clinton here is what I'm going to say is we are 95% confident that the true, or actually let's go with that the population percentage of people that will vote for Clinton is between 43.7% and 50.3%. Okay. And as a reminder, is what we mean by 95% confident is that 95% of confidence intervals formed using this technique, and for samples of the same size, 95% of those will contain the population percentage. Okay. Again, for what we're working on, we're going to be 95% confident that it contains the population mean. Okay. But same idea. All right. So let's go ahead and scoot down here. So the next thing that we're going to need, okay, and we may not know it yet, is Z star. So this is the formula that we're going to use for our confidence intervals. And so we have X bar, so that's the sample mean, plus or minus Z star, which is going to be really it's going to be exactly what you think it is. Okay, we'll go into more detail on it here in a second. And then sigma is our population standard deviation. And then we have divided by the square root of the sample size n. Okay. So there is one part of this that is not necessarily always going to be realistic. So we are trying to estimate mu, but you might notice here that in order to do so, we're going to need to know the population standard deviation. Okay? And what are the chances that we know the population standard deviation, but not the population mean? Okay. We will have a way around this. Okay? So for now, we're going to work with it with sigma there, but soon we'll figure out what to do, and we'll use the sample standard deviation. but we will no longer be using Z star at that point. All right, well, so let's figure out how we can get these Z star values, okay? So the Z star values are just how many standard deviations we want to go to the left and to the right of our sample mean, okay? And so, because remember up here, right, we designed the confidence interval to have a certain width. We wanted it to be a width such that 95% of the data would be. So I'm trying to say two things here at once. Okay. So that confidence interval that you're looking at in both of these pictures has the exact same width as that shaded region on the normal distribution. Okay. And so that shaded region on the normal distribution goes out enough standard deviations from mu in order to contain 95% of the data. And we're going to make our confidence interval have that exact same width. Okay. So that's what we're working with here. Okay. Trying to figure out how many standard deviations we need to go to the left and to the right. Okay. So, and you can notice here for 95%, this comes very close to what we saw with our empirical rule, right? This is essentially telling you that 95% of the data, or approximately 95% of the data, is actually within 1.960 standard deviations of the mean. Okay. But let's see how we can actually find one of these. Okay. So is what I'm going to do is have us move over to the right here in a second, and we're going to make a little picture, and we're going to see instead how we could come up with, say, the Z star value for an 80% confidence interval. Okay. Believe it or not, this is something you can already do. So we'll come over here. We're going to make our normal distribution. There we go. And I'm going to choose a very specific distribution here. Okay. I'm going to actually choose the distribution, normal distribution with mean 0, standard deviation 1. Okay. And so before we can actually get into this part over here, I need to explain why I'm using this one. So I'm going to make a second distribution right above that I'm eventually going to erase. I just want to motivate what we're doing here. Okay. So let's say that this is 7 and then this is 2. Okay. So this one up here would be centered at 7. Okay. And if you were to count two standard or 2 units to the right, that would be 1 standard deviation above, and we have 9. And if you were to count 2 to the left, that'd put us 1 standard deviation below the mean. So what that'd be 5 here. And you could label in and maybe another one if you wanted to. Here's 3, and then 11. And now if you were to write in the z-scores, right, the z-score for this one would be 0. The z-score for this one would be 1. This would be 2. Okay. So I want you to keep that in mind. And let's do the same thing down here for this one. I am going to eventually erase these dots here on this because I really won't need these for what we're about to do. Okay. So all I've done is I went 1 unit to the right and then another unit to the right, and I did the same thing on the left. But now let's find the z-scores for these. Well, 0 here is 0 standard deviations from 0, so this is z equals 0. This is 1 standard deviation from the mean, so this is z equals 1. This is 2 standard deviations from the mean, so this is z equals 2. So with this distribution, your z-score is the exact same thing as the x values that we have down here. Okay. And it's not the case for this one up here. Okay. And so the reason I'm doing this is going to make this one easier for us to work with. When we go to use inverse norm on this in a minute, which is what we're going to do, not only will it give us the X value down here, but it also will give us the Z score, okay, which is important because this is going to be filled with Z values, this table. Okay. And then if we did use this one, we'd have to do a conversion later on. And I don't want to do a conversion here. Here we go. Okay, so now that we know why we're using this one, we're going to try to find that Z star value for the 80% confidence interval. And maybe I'll just resketch this. Here we go. So yeah, if I want to contain the middle 80% of the data, let's try to visualize that. I just want this to look just a little bit neater. I guess that's good enough. Okay. So yeah, we want 80% of the data in the middle. And we want to find how many standard deviations that was that we had to go to the left and to the right. Okay. So we're going to try to find the Z star value. And again, in order to do it, we're going to use inverse norm. But we should also note that if the 80% is in the middle, then we have 10% in the tails, which should total to 100%. Okay. All right. So if we go ahead and use our inverse norm here now, is what I want us to know is for Z star here, what percent of the data is to the left? Okay. And if you total those up, you get 90%. Okay. So I'm actually going to put a 0.9 here for this area. And then I just need to put in the mean and then the standard deviation. And this will be the Z star value. Now, all the Z star values that I have in that table are rounded to the third decimal place. Let's go ahead and give this a try. So we want second vars number 3 for inverse norm. I want a 0.9 here, a 0, and then a 1. Okay. And I'll come down here and I'll hit paste. Okay. And so I'm getting here about 1.282 if I round that to the third decimal place. 1.282. And if we come and look over here, that matches exactly what's in the table. Okay. So you actually can use inverse norm to come up with all of these Z star values if you wanted to, but I will be providing you all with this table on the final. All right, so let's go ahead and attempt to use this formula. So if we come down here, it says a physical therapist is investigating the mean recovery time after ACL surgery for patients involved in a new therapy regimen. For the purpose of the study, a successful recovery was defined to be the ability to walk without crutches. For 38 randomly selected patients, the mean recovery time after ACL surgery was found to be 22.6 days. Assume the population standard deviation is 3.7. So if we go ahead and start writing down what some of these things are that we were given, for instance, we were given that there were 38 patients, so that's our N. We were also given the sample mean recovery time, which was 22.6 days. So that's our point estimate. Okay. And then we have our population standard deviation sigma. There we go. And let's go ahead and write down the formula that we need here for our confidence interval. It's X bar plus or minus Z star sigma over the square root of n. So that means the only thing we're missing here so far is z star. So all we need to do is go up and look at what the z star value would be for 99% confidence. So let's go ahead and scroll up and see what it is. So for 99% confidence, z star is 2.576. Let's go ahead and record that. Oh. All right, and that brings us to our next step. We just need to plug all these things in here. So our X bar again was 22.6. We have plus or minus Z star, which is at 2.576. And then we want to multiply that by 3.7 over the square root of 38. Right. And there is a nice shortcut that we can use on the calculator here for finding the upper bound, say, after we find the lower bound. So let's type in the lower bound first. So that'll be the one with the subtraction. There we go. Okay. Now, if I want to find the upper bound, I can just hit second and then enter. And then I can arrow to the left here. And once I'm hovering over the subtraction symbol there, I can hit the addition one. Okay. And I can go ahead and hit enter here. And now we have our upper and lower bounds. I'm going to screenshot this so that I can bring this into OneNote. There we go. And so let me record these and then I'll get rid of that screenshot. Okay. So yeah, our lower bound Okay, so for that lower bound, let's go ahead and just round it to one decimal place. So I'm going to say 21.1 days. And for the upper bound here, I'm going to say 24.1 days. There we go. Okay. So when it does come to these confidence intervals, you can be asked to write them in all sorts of ways. So one way is you could actually just write it like this. This is our confidence interval. Okay. One is you could explicitly give the upper and lower bound like this. Okay. And you can actually do this in another way. We have something called interval notation, which is a common way to write your confidence intervals. Where you use a parenthesis, you first write the lower bound, comma, and then the upper bound. Okay. All right, but we were asked to interpret this. Okay. And so this was a 99% confidence interval. So if I were to interpret this, which let me get a different color here. Let's see. There we go. Okay. So is what I'm going to say is that we are 99% confident that the population mean recovery time is between 21.1 days and 24.1 days. Okay. And again, is what this really means is that if we were to continue um, getting samples and recording sample means and then creating confidence intervals of 99% confidence, well, 99% of those will contain the population mean. Okay, so we could again have one of the lucky 99%, but we also could have one of the unlucky 1%. All right, and so we're gonna do the same thing here now, but for a 90% confidence interval. Okay, and so we have all of the information in this first line that we need. Very little is actually going to change here. So I think is what I'm going to have us do is just start at this step right here. Okay. I won't have us write that all down again. So we have our sample mean of 22.6. We have plus or minus. Now we need to find Z star for 90% confidence. So Z star for 90% confidence is this 1.645. And then we just need sigma and n. So sigma was 3.7, and we want to divide by the square root of the sample size, and that was 38. All right, so let's go ahead and get the calculator out so that we can plug this in. So what I might do is go take one of the original ones that I plugged in here and just change the Z star value. So this is 1.645. Let me just make sure everything else looks good there. Okay. So I'll go ahead and hit enter. So there's my new lower bound. And let's get the upper bound here as well. So let's go record these and then we'll talk about this a little bit. And so I might just write it in interval notation this time. All right. So our lower bound is about 21.6 and our upper bound is about 23.6. All right. So there's a little bit of a trade off that we've made here. Okay. So with the 99% confidence interval, we have a wider interval versus for the 90% confidence interval, we have a smaller interval. Okay. And so here's the idea is the wider the interval is, the more likely it is to contain mu. And the smaller it is, the less likely it is to contain mu. Okay. So, but if your confidence interval is extremely wide, um, it fails to be meaningful. For instance, let's just make a pretend here that our very first confidence interval, let's say that this went from 0 to 90 days. Okay. Well, that's not doing a very good job of narrowing down on the population mean. Okay. And this is kind of what can happen with these high percentage confidence intervals is sometimes they are really big. Okay. Now, the downside to the smaller confidence intervals is that we're less confident that they'll contain mu. Okay. So you'll always be kind of battling that confidence versus the size of the interval. All right. So we got one last one here. It says a social worker is concerned about the number of prescriptions her elderly clients have. She would like to create a 95% confidence interval for the mean number of prescriptions per client with a maximum error of 2 prescriptions, assuming a standard deviation of 5.2 prescriptions. What is the minimum number of clients she must sample? So when they say maximum error here, they're talking about our margin of error. And now we have a formula for the margin of error. Let's maybe write that down. And there is a good spot where we could add this in our notes. So up here, where's it at? Right here. The margin of error is that z star times sigma over the square root of n. So again, x bar is the point estimate. Once we add and subtract the margin of error, that gives us our confidence interval. So let's come back down here and we'll write that formula down. And well, as what we're going to do is we're going to take these two things and set them equal to each other. So I have 2 equals, and then z star for 95% confidence is 1.960. We know that sigma here is 5.2 prescriptions. And then we do not know n. So what we're going to need to do here is solve for n, again, in order to reduce the margin of error down to 2. So the very first thing I would do is actually multiply this 1.96 and 5.2. Right? So we're getting 10.192. There we go. Right? And then we could multiply both sides by the square root of n. And so if we do that, we get 2 square root of n is equal to 10.192. And then we could divide both sides by 2. So I'm going to come over here and hit divide by 2. So we're getting 5.096. And then lastly, we just need to square each side. So if we do that here, we're getting about 25.97. All right, so firstly, I want to point out n is supposed to be the sample size. This needs to be a whole number. So it may be obvious here that if we were to round this, we'd want to round this up to 26. But it actually ends up that you're always going to want to round up when you use this procedure here. Because if I were to round this down to 25, let's actually see what would happen. Okay. So I'm actually going to take this right here. Okay. And I want to point out, I want my margin of error to be 2 or smaller. Okay. I do not want it to be any larger than 2 here. So I'll take my 1.96. I'll multiply it by the 5.2. And I'm going to divide it by the square root of 25. Okay. I just want to show you what happens if you round down on these type of problems. Okay. You can see I've ended up with a margin of error that is not 2 or less. Okay. It's a little bit bigger. Okay. And so this will happen every time you round down. So you will always round up. And so if I make this 26, you'll see that it's now smaller than 2, which was the goal. Right. So yeah, remember that. For these ones where they say find the sample size to minimize the margin of error, you will round up. Even if this number was 25.1, you'd round it up to 26. All right. And so that here, this wraps up the confidence intervals for the population mean with sigma known.